Alright, so another thing we're going to do in 8.3 is write a complex number in polar form. So a complex number, we've already graphed the complex number as z equals a plus bi. You know, a is the real part, b is the imaginary part. Alright, so the polar form of this a plus bi is going to equal r times the cosine of theta plus I times the sine of theta. Alright, where r is the modulus. Remember, the absolute value of z was the modulus, and the tangent of theta is b over a. Alright, so this should be very familiar to you, so I want to look at it. So if I've got a complex number, right, we've got a plus bi, and I know that the distance from that origin is the modulus. In this case, they're calling it r, right? That's the square root of a squared plus b squared. I can drop a right triangle here and do what I've done before, where I'm looking at theta. I know that this horizontal distance is a in this case. My vertical distance is b in this case. So let's look at the relationship between theta and a and b. Alright, it's just like when we looked at the relationship between theta, r, and x and y, when we were going from rectangular to polar, from polar to rectangular. Now we're going from complex to polar, but it's really all the same thing. Because if I was looking at the relationship between theta and a, I would know that a is my adjacent. I've got r defined as that modulus, so I've got the cosine of theta equals a over r, or a equals r times the cosine of theta. Right? Likewise, I've got the sine of theta equals the opposite, or b, over r, so b equals r times the sine of theta. Right? This was just like if a were x and b were y, if I was talking about rectangular. Now I'm talking about real and imaginary, but it's the same thing. And so what I've done here is I've taken my imaginary part, z equals a plus bi. Well, I just came up with what a is. A is r times the cosine of theta. B is r times the sine of theta times I. So all they did was clean up this formula. They factored out an r and came up with polar form is going to be r times the cosine of theta plus I times the sine of theta. Alright, so what we need in order to write complex into polar is r and theta. We know how to find r and theta. We've been finding r and theta when we did rectangular. Now we're doing it for complex. Okay, so in this case, I've got a equals 1. I've got b equals negative 1. All right, how do I find r? Well, I know that r is the absolute value, or the modulus, and I know that's a squared plus b squared, or in this case, 1 plus 1, which is the square root of 2. All right, the next thing I have to have is theta. All right, so this is the important note, always. When we're looking for theta, you have to pay attention to what quadrant theta is coming out of. All right, so if I'm looking at the graph of 1 minus I, think about where that would be. I would go over 1 on the real axis and down 1 on the imaginary axis. So I'm in quadrant 4. All right, so my theta is coming out of quadrant 4. So when I find tangent of theta is b over a, or negative 1, I know that the tangent of theta, I know that my reference angle is 45 degrees. And from quadrant 4, I've already determined it's coming from quadrant 4, is going to be 360 minus 45 degrees, or 315 degrees. All right, so I have r, I needed r. I have theta, I needed theta. So now all I have to do is write this in polar form. So z is going to equal r, which is the square root of 2, times the cosine of theta, which is 315, plus I times the sine of theta, which is 315. And that is taking a complex number and writing it in polar form. All right, you leave it just like that. Let's do another one. All right, I've got to find r and I've got to find theta. Let's talk about what quadrant this is in first. So I'm going to the left and then up. If I'm going to the left and then up, I'm in quadrant 2. All right, important. Determines where theta is. All right, to find my r value, I know that that's the square root, that's the modulus, that's the square root of negative 2 squared plus 2 squared, which is going to be square root of 4 plus 4, or the square root of 8. All right, to find theta, I do the tangent of theta equals b, and maybe you should write out. So a is negative 2, b is positive 2. All right, the tangent of theta is going to be 2 over negative 2. I know that's coming from quadrant 2. I know my reference angle is 45 degrees. So from quadrant 2, I'm doing 180 minus 45 degrees, which means my theta is 135 degrees. So to write this complex number in polar form, I've got z equals r, which is the square root of 8, parentheses, cosine of theta plus I times the sine of theta. Okay, let's do one more. What's A? A is negative 3. What's B? Don't have an imaginary part, so it's 0. And maybe we don't even have to do a lot of work here. Think about if I were graphing this, what it would be. If I were graphing this, I would go down 3, to the left 3 on the real axis, to the left 3 on the real axis, and not up or down on the imaginary axis. So that is where that complex number would be. So I don't even think we need to use a formula to find an angle. Hopefully you don't. What is r? We don't need to use it to find r or theta, because the distance from the origin is 3. My angle over here is 180. I will confirm it though. So if I were looking for r and you weren't graphing it and you were just kind of going through the motions, you would say r equals a squared plus b squared, which is 3. Tangent of theta would be 0 over negative 3, so the tangent is 0. And you would have to think about where that was, because it could either be at 0 or 180, so you need to be careful with that. So writing this in polar form, I've got z equals r times the cosine of 180 plus I times the sine